Okay, 1
to
hour.
your disposal.
I've already got my timer running, so I'll leave some time for questions.
This is the first time that I see this.
Yes.
So, the
Yes.
floor is yours.
Yes, well, thank you very much, Klaus. Thank you for coming to NIST and finding me back in 2016. This is my third trip to Germany now to give a talk on NIST-on-a-Chip and related things, and I'm really excited that you guys are here today in this, I think, really exciting measurement fair. So I'm just going to jump right into it. Jay Hendricks, Deputy Program Manager, NIST-on-a-Chip, and I manage this program with Barbara Goldstein, who's the program director. So I'm not going to spend much time on this outline, but this briefly talks about what you're going to be hearing about today. I'm going to introduce the NIST-on-a-Chip program. It's a short 1-minute video. I'm going to talk a little bit about why we care about measurements and standards. And I'm going to talk a little bit specifically on what NIST is doing for making measurements such as pressure, vacuum, temperature. And then there's a video at the end that's about 3 minutes long that talks about our search for partnership and collaboration. Okay, so we're going to jump right into it. So I come from NIST Gaithersburg. For most of you probably aren't aware, NIST actually has 2 campuses, and one of them is in Boulder, Colorado, not too far from Denver, and the other one is on the East Coast just side of Washington, D.C. So I come from the Washington, D.C. branch. Before I get into too much, I thought a quick little video that basically explains the NIST-on-a-Chip program, what you're going to be hearing about today. So, before I show that video, though, I do want to let you know that there are a few things that you probably know NIST for, and that is our measurements that we do, but we do a lot of basic research as well. And the NIST-on-a-Chip program falls within that sort of researchy part of the program. We do calibration services, so a lot of folks in the United States as well as in Europe and worldwide will come to NIST for specific measurement services. Of course, here in Germany, you can go directly to PTB. NIST and PTB are always sort of trying to see who can be the best at what we measure. So this is what we call a friendly rivalry, and we like to think of ourselves as sort of the top 2 brands in the metrology space. Okay, so for the AV, I am going to show a video, and hopefully everything goes smoothly. Here we go.
Technology has changed over the years. It has gotten smaller, more affordable.
And our AV guy is out right now? Yeah, so we do have a sound issue, so I'm going to back this up. And
You have a mini check?
yes.
Mini check.
Yep. Okay, good.
Technology has changed over the years. It has gotten smaller, more affordable, more mobile. These advances demand a new era of measurement science. Introducing NIST-on-a-Chip. These devices will combine the latest advances in metrology with the latest advances in technology. They will make the most precise measurements in the world smaller, affordable, and most important, based on quantum standards NIST has pioneered for decades. You will be able to take NIST with you, anywhere, at any time. It's up to you where these devices will go and what new frontiers they will allow us to explore. Partner with us and be part of the metrology revolution.
Okay, so that briefly gives you a quick sort of overview about what I'm talking today. So I think it's really cool that we're in a sensor and test measurement fair, because this is exactly the kind of place where we'd like to sort of push this message out. This idea that you can create sensors that in many cases are going to be quantum-based. What's really super valuable about these quantum-based measurements is that they don't require additional calibration, because you're looking right into the face of nature, as it were, and getting the measurement directly from the physics. We think it's particularly powerful when these technologies can be made very manufacturable. That's where technology comes in, because a measurement is really wonderful, but if it's in the lab and it's full scale, it's not very useful to most people. What you want are things that are, in your phone and very easy to use and get directly out into the world, right to the end user. In terms of sort of like, why do we care about metrology? I really love the airplane as an example. If you've gotten on an airplane recently, you probably want to know that the sensors that are flying that airplane are giving the right, accurate results. This is incredibly important, not only to just the performance of the aircraft in terms of efficiency, but also to your safety as well. In fact, just last year at this conference, there was a talk from Airbus, and they were pointing out the complexity of the modern aircraft. And what was being talked about here was basically the heating and air conditioning system on the plane. And you might think that that's a pretty mundane thing, but this is such a complicated thing when you're up in flying at 30,000 feet, because the air pressure is quite low. So you have to actually get the pressure in the plane exactly right. If it's too low, the plane could implode. And if the pressure stays too high as you descend, or gets too low as you descend, it could either implode or explode on you. And so this is an example, I thought, where, in your house, you don't really worry about your air conditioning system, but in an airplane, everything has to work exactly as it's supposed to. In terms of where metrology is, I don't think I have to sell you guys on this too much here, because you understand the importance of metrology to economy. In the United States, we had our economic people look at it, and there was roughly $14 trillion in US GDP that is linked back to measurements that come from national metrology institutes, such as NIST or like PTB if you're here in Germany. So I'm going to talk a little bit about standards and the problem with standards. Pretty simplistic view, so I'm going to use a clock. So we all know what a clock is, and if you have one clock, in general, you know what time it is. The problem comes in when you get a second clock, and it's not quite giving the exact same answer. This is what we find when we do any sort of measurement. And so this is the point that we're trying to make, that you have to have standards that agree, or at least agree to within the fit for purpose. If the trains are running 10 minutes late all the time, maybe it doesn't matter that your clock is 5 minutes off. But if they're running down to the minute, you actually want to get to the platform when the train arrives. Let's talk a little bit about clock evolution and sort of how we've got to where we are today. If you go back in time, humans have been trying to keep track of time for pretty much as long as we can go back and look at our history. So shown here is an example of Stonehenge. And I'll ask you, is this terribly accurate? No. Will it tell you the nanosecond that you're at? No, it won't. But will it tell you what day of the year it is? Yes, it will. And for the people that built this particular clock, this was incredibly important for, say, agriculture. So this is a case where they had a metrology tool, and it was fit for purpose. It did what it needed to do for the reason that it was built. Now, as we look at clocks and we go through the evolution, we get to a mechanical age where now we can build things out of gears. This is around the 1700s, and clocks are getting much, much more accurate. Sort of a major jump occurs when we invent the quartz crystal oscillator, because now we can get time down to sort of millisecond drifts per day. When we go even farther, you can go to the chip scale atomic clock. So I don't have a slide on this, but at NIST, there's an entire lab set up just to make measurements of time. and you can do it to a part in 10 to the 18th, which is incredibly accurate in terms of the clicking of the clock. What's shown here on the screen is a chip-scale atomic clock that's made from cesium atoms, and it's good to about a part in 10 to the 8th. What's really important about this clock is that it's portable in the sense that it can be put into, say, a cell phone tower. At a case where a lot of people maybe realize or not, the timing is really important in cell phone towers because packets of data go out from your cell phone, but they can get picked up by different towers and retransmitted, and then the packets arrive, and they're all stamped with a time code from the individual towers. Well, to make that all work, all the timing has to be actually pretty accurate down to the split second. And if you've ever had a dropped call or information not coming through, that's a case where either the data is not being transmitted or it's being transmitted out of sequence and is rejected when it gets to the source. Okay, so about 5 years ago, a major thing happened with the way that the National Metrology Institutes around the world actually realize our basic units. So under the old definition, there you see this colorful wheel, and that colorful wheel under the old SI for second, mass, ampere, Kelvin, candela, mole, and kilogram, a lot of those artifacts were used to realize things such as the kilogram, or in the case of temperature, it was triple point of water cells. So when we go to the new SI, what happens is some things change. For example, the triple point of water is now replaced with something called the Boltzmann constant, and that's how you're going to realize temperature. And for mass, you're going to use the Planck's constant. Why is this important? Because it really does change the way that we can think about the units, and it changes the way that we can make sensors that access those units. So for example, for pressure, which is the Pascal, having temperature in Kelvin defined means that now we have pressure defined in terms of fundamental physical constants, whereas before we were based on artifacts of triple point of water and a lump of metal that was being held in Paris. So why is this important? Well, it democratizes metrology. If you don't have access to the kilogram in Paris, you can now just measure Planck's constant directly, and I have a few slides that talk about that. And it often also changes our problem into just what we call a counting problem. And I'll talk about this cold atom vacuum standard that's used for measuring vacuum, and it explains why that works. And I think this is the really powerful message. When this is done well, and it's done at the sensor level, it means that you have sensors that don't require recalibration. They either work or they give no answer at all. All right, so now I'm going to take a little mini deep dive into making measurements of pressure. And the teaser there is, how can you do it using light? And the answer is, and then what I'm going to talk about for the next few minutes, is the fixed length optical cavity. So if you want to make pressure measurements, for the past almost 400 years, we've been using mercury barometers to make those measurements. And about 10 years ago, we started at NIST on a project that's going to use these fixed-length optical cavities to make pressure measurements. So this is an article that showed in Nature that talks about the work that I was involved in at NIST. In terms of the timeline of how we got to where we are with mercury barometers and pressure measurements, what you're seeing up there is Evangelista Torricelli in 1643 inventing a mercury barometer. He's actually playing with mercury and a glass tube. He has a bowl of mercury and a glass tube. He seals one end of the tube so it's like a cup, and he fills that tube all the way to the top with mercury. He puts his thumb over the top and places it underneath the surface of the bowl of mercury, releases his thumb, and then holds this 1 meter long glass tube. And when he notices that he makes that glass tube more than 1 meter high, there's this little gap that appears at the top. It doesn't matter how long he makes the tube, it's always the exact same height between the bowl of the mercury and the gap. So as we now know that that gap is called a vacuum, so he not only invents a barometer for measuring pressure, he also invents the concept of vacuum in terms of the getting rid of all the gas in a system to create a pressure-free zone. Now at NIST, I actually started at NIST almost 30 years ago, and this was a picture of me earlier in my years, standing next to this tall column that looks like part of a building. That's actually a 3-meter high mercury barometer, and we use that to make our national pressure measurements. So around 2018, though, we have now switched over to this optical method, and what's exciting about this is that it's going to be based on the quantum properties of the gas. In this particular case, we're talking about the refractive index, and when that gas is easy to theoretically handle gas such as helium, you can actually calculate the refractive index from first principles quantum chemistry calculations. So fast forwarding now to the present day, what we're seeing on your screen is a prototype device. It's about the size of a sugar cube, a very large sugar cube, you know, so smaller than a Rubik's Cube, but bigger than a sugar cube. And it enables us to measure the exact same pressure range as the mercury barometer, but doing it with light, basically lasers bouncing back and forth in a cavity. And I'll show you just a little bit more of the technical bits of how it works. So what we're going to do is we're actually going to build a piece of glass. What you're seeing there is ultra-low expansion glass. This was the NIST large prototype that we built. And we put mirrors on the end, and when you get a resonance between those mirrors, you know that you have an integer number of 1/2 wavelengths in the cavity. Now what happens is we keep one cavity of vacuum, so the length won't change. And the second one, we add a gas. And when you add the gas, it causes the speed of the light to go slower in the vacuum, or in the air. And in that speed change, because it's now in air, actually results in a different wavelength. So what happens is you start to lose the lock on the cavity because you no longer have the Fabry-Perot condition. What we can now do is tune the frequency of the input laser just ever so slightly until we're back on resonance. And what that does is it means that we've wavelength locked that cavity. Pretty basic laser physics. What's amazing is how well it can measure the number density of the gas particles in that cavity. I have to say I was actually pretty amazed when I saw the first data, because it will work all the way down to 10 to the -7 torr. So that is actually a pretty good vacuum. And the reason why it works is that we're looking for such a small difference in the length of that cavity, and lasers are so good and things are so stable that you can actually make that measurement down to where I would have thought it was impossible. Okay, so here's a little video animation of what I just showed you. So think of the top cavity as having the gas, and the bottom cavity is now at a vacuum. And on the graph over there, you see a pressure gauge. And now what we're going to do is I'm going to start the animation. You're going to see the pressure go up. And there it goes. And what happens is we now have to change the frequency going into that cavity. What we're going to do to make our math much easier is we're going to do something called the beat frequency. And all you do is you subtract the frequency of the stable vacuum cavity from the measurement cavity. And now instead of trying to make measurements in the megahertz range, you're making measurements in the kilohertz range. So what do we have? We have a pressure device that uses light and, as its primary output, uses frequency. And as you know from sensors and sensing technology, the frequency space is a delightful space to be in if you want to make a measurement. And as I point out, we've been working on a collaborative research and development agreement, that's called a CRADA, with an industry partner. And they've got a device that's shown there with a pencil for scale. So you can see this is getting smaller and smaller. It is our hope that this could wind up, you know, at a trade show in a small package that you could pick up and use right off the bench and have a pressure gauge that does not need recalibration. Okay, so that's how we would do pressure measurements, sort of in the low vacuum all the way up to several atmospheres of pressure. But the question becomes, what if you want to go even lower in pressure, down into really, really hard vacuums? We're talking about the vacuums that occur in space, or the vacuums that occur in the interstellar spaces. Why are these important? Well, I'll talk a little bit about that in a second. But first I want to show you what this looks like. That blue arrow is pointing to a dot, And that dot is several million lithium atoms that have been laser cooled and trapped in something called a MOT, a magnetic optical trap, to within about a few millikelvin. And when that is done, you actually have this sort of new state of matter that you can use for an experiment. And you would think that this was hard to do, but I'm going to show you that while it starts as a laboratory scale equipment experiment, with innovations in technology, you can make this down to a portable device that you can hold in your hand. All right, so why is making really, really low pressures important? Well, if you think about like the semiconductor industry, they want to make chips, and they want to make chips in an environment where they can control the gas species that are in there, and you want to be able to have the chemistry under control as well. So it turns out in vacuum science, there's a unit called the Langmuir. And what is a Langmuir? It's if you wait 1 second and you have a sticking probability of 1, that is, every time an atom hits the surface, it sticks and doesn't move away. It will take 1 second at 10 to the minus 6 torr to completely cover your surface with that gas. Now, if you want to do the process, that's great. But if there's some kind of gas in there you don't want, you want to know that it's not in there, or your surface chemistry is being affected. So, you know, in fabs, they know about the chemistry, they know about the physics, and they're always playing with things to make it work for their process. The point I'm trying to make here is even if you get down to a really, really good vacuum, and what's a really, really good vacuum? Like 10 to the minus 10 torr. Well, even at that pressure, you're still going to have, when you do the math, over 1 billion collisions with a 1 centimeter square surface every second. So you think it's a low pressure, but it turns out there's a lot going on even at a low pressure. Okay, so moving on. How does this work? So what we do in this particular experiment is we get a cloud of lithium atoms. You can actually do that pretty easy. By heating up some lithium metal in a vacuum and make the atoms evaporate, and then you can make them into a little beam, and then you can trap them using this magnetic optical trap, which I'm not going to go into a whole lot of terms of how it works, but if you're interested in that, pull me aside and I'll give you a mini lecture on how to actually trap an atom. What's really cool about this is that now you've got this trapped atom at a very, very low temperature. So any other gas particle that comes flying in there and hits the trap is going to be about the temperature of the wall that it bounced off of. And in at room temperature, that's like 300 Kelvin. And now it's coming into a trap that's a few microkelvin. What's going to happen? It's going to eject with almost unit probability for 1 molecule of gas for 1 trapped atom. So how are we going to use this to make a vacuum measurement? Well, it turns out that that little dot with the blue arrow, with about 1 million lithium atoms, you can actually use just a regular old CCD camera, and it can tell the change in intensity down to the level of a few atoms leaving the trap. So this is the part where now it's just a counting problem. You want to know the pressure? You just count how many atoms you're losing from the trap based on the background gas pressure. So I have, again, a couple animations that I'm going to show you that sort of show you how this works. So the red molecules are the hot gas coming off the chamber wall. It's going in, it's hitting the trap, and it's going away. How will that trap decay? It's going to go by this nice Arrhenius plot, where it's e to the minus t over tau. So that emission intensity is just going to drop down. And the researchers that do this, you can video it on your phone, and he says that you can take that home, and with a piece of graph paper, you can get the pressure of that experiment to within 20% just looking at your phone and looking at the intensity of it. So that's how incredibly important we think this technology is. So here's an animation showing that when you turn on the 2D MOT, you can see the atoms appear. And when you turn it back off, the atoms just disappear. And it's that disappearing that's telling you what the pressure is. What's really cool about this particular technique, usually the lower the pressure gets, the harder the signal is. It turns out in this case, because the signal is the amount of time for things to disappear, you actually get more data at lower pressure. So it works better at lower pressures. It actually doesn't work as well at the higher pressures where the fixed length optical cavity works. So we like these two technologies because they have this nice trade-off in terms of where they work. Okay, a little bit more about how you make a measurement. Again, it's all about the fluorescence that you're measuring in the trap. You turn that fluorescence into a number of atoms. You fit this to a curve that you've previously created in just basically a database, and voila, pressure measurement. If you're interested in that, the reference is there. Okay, so the full-scale device takes up like a laser table that's a good part of this stage, and has lots of complicated lasers all around it. Not very portable, not very sensor-like. But the team has been working on a portable version, and what's shown here is a quarter with a diffraction chip. That diffraction chip is important because it's going to reduce the number of lasers that we need to make a measurement. And I have an animation that shows that. So they've basically redesigned the head. It's now about the size of this water bottle, no longer taking up an entire lab. Little details about how it all works. It's got magnets on it. So here's the animation of how that diffraction chip works. So you've got atoms coming up from underneath the chip. So the chip is that blue line. You notice there's a hole in the center. That hole is very important because the atoms are going to come up underneath with momentum, and the laser coming down is actually going to slow the atoms in the opposite direction, allowing them to be trapped. So normally you would need a laser going down. You need one from the left. You need one from the right. You need 6 lasers to do this. What's incredible about this chip is now we're going to use one laser. It's going to come down. It's going to strike that diffraction grating. And it's going to diffract and go up. And it's the diffraction of all those lasers that now makes that one laser do the work of 6. And so now we've gotten from 6 lasers down to 1. There's a little video of it working. I'm going to run the video. Maybe you're going to see it. Keep your eye on this area here. That's the lithium trap. This was shot just using a cell phone. I held it up to the vacuum chamber and hit play. And what you're seeing there is this little wisp coming and going. That's the lithium cloud. It works. Great. Shown here is a scientist. This was last year at a metrology conference, and he was holding in one hand an ion gauge. That's the way that we make vacuum measurements today. And in his right hand, he was holding a prototype of the cold atom trap. So we've now got a device that's about the same size device as the commercial device that would not need calibration. In the case of the ion gauge, it has to be calibrated. If you send it to NIST, it'll cost about $10,000 or $15,000 to have it calibrated. And if you bring it back and you bump the box, it's going to change the position of the filament, and now you're going to have it recalibrated. These cold atoms, they don't have that problem. They're based on nature and physics, and like I said, now you've got a vacuum measurement that is just a counting problem. Okay, so that's pressure. What about temperature? Temperature is pretty important. So it turns out that we've got work underway at NIST to make measurements of temperature with photons. Okay, so shown here for scale are 3 different magnifications. The picture is actually showing a coupler going down to a chip. That's on the scale of a millimeter. But if you zoom all the way back up, what you're seeing is this small microstructured device. Turns out that's another Fabry-Perot cavity. So you can send light into it, and it's going to bounce back and forth in the Fabry-Perot cavity. Now those little holes are going to change the refractive index of the device, and so as the temperature of that little microsilicon beam changes its temperature, it's going to be incredibly sensitive to the resonant frequency, again, in the Fabry-Perot cavity. So once again, we're now making a temperature measurement, and we're not doing it with electrons, we're doing it with photons, and we've got a device that is incredibly accurate for measuring temperature. So a little bit more about the temperature scale. as you may or may not know, there's something called the ITS 90 scale. It basically works because of the fixed points. A fixed point is a physical artifact, like a lump of tin freezes at a certain temperature. A lump of gold freezes at a different temperature. And by putting all those fixed point scales up there, that's the temperature scale that we all use. And here's a dirty little secret, or maybe it's not that dirty, but the ITS 90 scale is still used today, even after unit redefinition. Why? Because it's so convenient and it works well. So we didn't want to change, the metrology institutes didn't want to change something that works well. But again, to be traceable, the temperature, all you need to do is go back to Boltzmann constant with a check-in. What we like about this, this sensitive photonic thermometer, which we call SPOT, is that because it's made out of silicon and uses photons, it doesn't drift like the sensitive platinum thermometry, or SPRT, which is made out of platinum wire, where the metal boundaries can kind of crystallize, and so the resistance of it can change. And if the resistance of it changes, it also has to go back and get recalibrated. So what we like about SPOT is once it's characterized, when manufactured, it would never need recalibration again. In terms of the scale, this is a picture of a knot tied in a human hair, and this is a picture of the photonic thermometer, and it turns out you can fit, wait for it, a lot, thousands of these thermometers on a single human hair. So this is something where the actual sensor is incredibly small. What we are going to have a challenge with this technology is getting the laser system and the connection to that sensor down in size. But that's an area that we think we need future work on. In other words, if you look a lot of the NIST-on-a-Chip program, we've got something that works on this big laser table scale and all this complicated electronics. So what are the things we need? We actually need to start focusing on things like on-chip lasers and integrated photonics so that you can get all this stuff from big clunky pieces of equipment that are in your lab down to a single sensor head that's just going to make the measurement that you want to make. In terms of performance, the red graphs are the state-of-the-art platinum thermometer, and the blue graphs are the sensitive photonic thermometer. And the takeaway message here is our preliminary results show that it's got a measurement accuracy that beats, in some cases, or is just about as good as the sensitive photonic thermometer. And we've been doing research on how you make this bonding to chips. Again, this is just glass. So once you figure out how to do it, you can mass produce it, and you can do it cheaply. And it doesn't require expensive metals like platinum. And again, what we're doing to make these measurements is we are just, as we ramp the temperature, what happens is we get different frequencies. And so you can basically tune on a particular device, and once you've done that characterization, again, you've got a photonic means for measuring temperature. Okay, so I'm going to spend less time on these next two things, but I think they're important. Mass, and how do you make measurements with Planck's constant? I'm not going to give you the how-to. There's some great web pages out there. But what's really cool, again, is you're going from this big you're going from a lump of metal in Paris to not very useful, very big piece of equipment at NIST. So shown up there is something called the NIST-4, and that is our realization for the Planck's constant. And NMIs from around the world got together when we wanted to define Planck's constant, and now it's fixed. So you can no longer say that you're going to measure Planck's constant because the uncertainty on Planck's constant has been assigned to 0, and now all you can do is make a measurement of mass. This has real implications, however. Now, if you want to measure mass, it's really an electrical measurement. And I've been thinking about this. You think of an electric car when it stops or when it goes up a hill, where you're just taking electrical energy and turning it into changing the momentum of that car. So in a way, if you could do better and better measurements, you could actually measure the mass of your car just from measuring the electrical inputs that you're putting onto its load. I think it's pretty cool. What's gone on with mass? We've been shrinking it. And shown up here is sort of the evolution. So entire lab. Then we go to the middle screen. It's about this big. And now the final screen, it's something kind of like this. And again, this is requires an actual mechanical beam balance to do the measurement. But what's cool is that you would not need to add calibrated masses to this. You get rid of the entire calibration chain. And actually, the Department of Defense in the United States is actually funding work, and the delivery of one of these devices was actually sent out to one of our military institutions because they think this is super important for their metrology programs to become self-calibrating and really get into the NIST-on-a-Chip vision. Okay, so balances are us. We've been making balances and making balances. Sometimes when we go to trade shows, we actually bring a version made out of Legos, and you can make a pretty good mass measurement that's linked to the fundamental principles of the Planck's constant using a Lego balance. Again, it all comes down to the accuracy of the voltmeters you're using and so on as your inputs, but the point is you've got like a little miniature NMI right there. I'll spend even less time on this, but another example of something that you wouldn't want to calibrate is a radiometer that you put in space. And you could put radiometers in space so that you get very accurate measurements of like the conditions on the planet below. You want to know like cloud cover, you want to know like how much light's hitting a surface. Radiometry in space is incredibly important. So what we've done is we've come up with a device that has been launched and will never come back for recalibration. And so far, it's been working quite well. So this slide is just put in to sort of point out we are actually doing some of this stuff. It sounds like science fiction, but there are real examples, chip-scale atomic clock, radiometers in space, where this is actually happening today. And this metrology revolution, we think, is coming to the showroom floor within your lifetime. So stay tuned to this because we think it's a really exciting area to watch. A little bit about the difference between making measurements in the lab and what a sensor does. There's a slide that we put together that sort of basically just tries to figure out what is a sensor and what does it do. But what I think is really interesting is that it's just creating data that allows something else to take an action on that data. And that something else could be a person. It could be a machine. So you could think of AI, or it could be another sensor that's making another decision about something. So I think this is really important when we think about how the complexity of things move forward and watch this space. So audio, we are going to start another video. Okay, here we go.
Measurements, technology, and innovation are all inextricably linked together. You can't advance technologies without precision measurements.
The vision of our NIST-on-a-Chip program is to create a suite of tools and sensors that are fit for purpose, small, precise, and portable, and never have to be recalibrated.
So the concept of eternal traceability, that calibrated once and never has to be calibrated again, that's an exciting concept. That could have applications in outer space. It works very well in our military where they have to be out on site. If you're in a submarine, you can't just turn around and come back to port because your instruments are due for recalibration.
Well, as your instruments are deployed farther and farther out, which they are farther out into the solar system, then it becomes more difficult to calibrate against ground-based measurements.
Planes right now are roughly 50% plastic, but we don't know how long they're going to last. And if we can take sensors and embed them into those structures and do real-time monitoring for fatigue, well, then we've got a whole new way of thinking about maintenance.
And if the process can be done faster, more efficiently, then we have to buy fewer aircraft because they're not out of service for as long a period.
But sometime in the future, these ultra-precision measurements will enable us to make measurements that are so precise that an atomic clock will be able to probe gravity waves. That would allow us not only to observe distant events like black holes colliding with each other, but allow us to observe what's going on inside the Earth that causes earthquakes and volcanoes, and where water is located under the Earth or where oil is located under the Earth.
In biotech, for example, the ability to precisely monitor the temperature of vaccines is very important. Imagine if we could embed a NIST-on-a-Chip temperature sensor on every vial. We could help ensure the quality of delivered vaccines.
We know that this is not just science fiction and only futuristic, because we have already success stories that fit this paradigm.
But we're looking for partners to explore what we know are endless possibilities for how we can translate these technologies into practical devices.
Okay. So that's part of the reason why I'm out here today, is really to sort of spread the word in terms of what we're trying to do at NIST. And we are actually looking for partnerships. And what's shown on this screen is many devices that we currently have out there that we're looking for industry to partner with. And some of them we were already engaged in partnerships, but let that be said, that if you see something up here that you're interested in, come find me. I'll give you a business card, and we can start that conversation. I do just have like 3 or 4 more slides. So in terms of like the NIST-on-a-Chip portfolio, this slide is actually probably old in the sense that I think there's probably more than 60 projects that we now have running. I love the program because I get to work with some of the best and brightest at NIST. And they're just coming up with all sorts of innovative solutions to a whole host of metrology measurement inputs. And it's something else I want to mention is that because we're a National Metrology Institute, we think in terms of that colorful wheel of mass and temperature and so on. But there's so many other sensors out there where we think the NIST-on-a-Chip idea can work, that's important as well. So think of like sensors for momentum, inertial change. This is all really super important because it's part of what makes a complicated system work. Particularly if you start thinking of like autonomous vehicles, self-driving cars, and so on. They're going to be loaded with sensors, and they're going to need a variety of different paradigms in order to make the device work as planned. So the big vision of NIST-on-a-Chip shown sort of there is that it's really at this unique time. We've got the redefinition of the SI coming along. I've mentioned the importance of nanomanufacturing. That's what it makes it cheap. This idea that the quantum 2.0 revolution is happening, that means that we can now take advantage of quantum properties to make new sensors. And at the time when industry is looking to automate systems with AI and so on, and Industry 4.0, we really do see this convergence of technology really accelerating around programs like NIST-on-a-Chip. In terms of what this means for the National Metrology Institute, we have to think about what our role is, because we've always been the ones where you send stuff in, we calibrate it. What happens in this NIST-on-a-Chip world where everything is out in the field and isn't coming back? And that's gotten a lot of interest out there. I don't think the National Metrology Institutes are going away, because one of the things that NIST-on-a-Chip doesn't replace is quality assurance. And so while you may have a sensor that doesn't require recalibration, you still need to have a quality assurance program that says that your process is doing what it's supposed to do, and it's not failing by the ways that things can fail. And it could be in complicated ways like training of the staff and how they're using it. And so to the extent that we have not got a NIST-on-a-Chip replacing the people, there's going to be quality systems out there well into the future and my retirement. So with that, I'd like to thank you for your attention, and I'm thanking some of the authors of work that you saw up here. There's many others at NIST, and if you would like to reach out to me, you can find me at jh@nist.gov, on LinkedIn, or on X. Thank you.
I thank you, Jay, and thank you for coming here, for coming over. So I think it's absolutely impressive.
Thank you.
I think your more or less last comments here, that we also in the future need the quality assurance program, is very important.
Absolutely. And if you think about
also, also for our feeling.
Yes. Very much so. Yeah, I was going to add, like the talks that we saw on the digital calibration certificates, this is sort of part of that quality system that isn't going away, but those digital calibration certificates are sort of part of that NIST-on-a-Chip vision, that buried underneath that technology, you would have a traceability certificate.
2 questions. The first one to the mass, the Kibble balance. What about the silicon path to the mass?
Yes.
Because I was responsible for the Avogadro's constant in the Eastern Bloc.
I agree. And
past.
there's nothing more beautiful than a silicon sphere that you hold in your hand.
Yeah.
So in terms of like beauty and simplicity of concept, I really love the silicon sphere methodology. I think what's powerful about the Planck's constant is that it takes you from this artifact, which is, again, beautiful, and puts it into an idea, a physical constant. So for this, yes, because there was a little bit of a, for those of you who don't know, PTB was focusing on the silicon sphere, NIST and others were focusing on the Kibble balance, so this is part of that friendly rivalry that we talk of.
In my home office, I have a silicon sphere.
All right.
So another question, if I go back to pressure and vacuum.
Yes.
Is there initial test? Maybe the vacuum is not good enough or something like that, or just for my human feeling. I'm a guy who heard something about metrology and so on, but not too much. So how to rely that I can really rely on the values they come out? Is there any initial test or quality program?
Oh, in terms of the value, like the cold atom. So the cold atom, we have compared, we're building an entire system called an orifice flow standard. For the metrologists out there, that is where you put a known amount of gas through into a chamber, and by the process of division, you can calculate the pressure very precisely. And so using that technique, we've been doing comparisons directly against the cold atom vacuum standard. And so far, everything is working great. In other words, we will have a complete conversion from the old scale to the new scale. And the uncertainties of the new scale should wind up lower once we're done. In the case of the fixed length optical cavity, we've done head-to-head comparisons with the mercury manometer. And there, what we actually see is some artifacts that we now know are coming from our mercury manometer in terms of sort of the shape that you get from the comparison. Right now, the mercury manometer is slightly lower uncertainty than the fixed length optical cavity, but that's because we, as a community, need to work to get better values for the refractive index of gases. And in the case of the fixed length optical cavity, we want to use nitrogen. And when you use nitrogen, the refractive index right now has been, the best one has been determined by NIST, and it's been done using the mercury manometer. So we can't go below the mercury manometer in uncertainty. However, once the world figures this out, any country, anywhere, can come up with a better number of the refractive index. We all plug it into the same device, and we're all completely traceable. So it's a beautiful thing. So to answer your question is, yes, we've done comparisons for both CAVs and flock, and the results are very promising and good.
Maybe one remark. A couple of years ago, I think 5 years or 6 years ago, I heard the first time about the NIST-on-a-Chip. It was in California. Somebody reported to me. And then I read that one of your sensors was more accurate, more precise than your standard in the US. So,
yeah, you always.
I was really surprised.
But how do they know, right? That's always the question, right? But continue. Yeah, you were surprised. Yeah.
No, I was really surprised. How can this happen?
Yeah. Oh, I see. Yes. The speed at which this science fiction is happening it's happening fast. Just like AI has kind of shown up, and all of a sudden everything's AI. I think sensors and sensor technology combined with AI is going to be a very interesting space to watch. 100%.
One last question is not so very discreet. What is the volume of the NIST of a ship on a ship program?
What is the volume? You mean
money.
Oh, in money? In money, it's about a $10 million program, internally funded each year. So it's been running for over 10 years. So about 100 million U.S. dollars have already gone into NIST-on-a-Chip. What's impressive is if you look at how that money has been leveraged with other money, it's double, triple, 3 times the size coming from other agencies and basically other work at NIST that would be going on anyway.
But when I look at AI,
yes,
this is much more.
Yes.
No, thank you very much.
Thank you.